Okay, class, welcome to lecture 24. So today we're sort of jumping into completely new territory. We're going to be talking about linear regression. So a lot different than the hypothesis testing we've been doing. You can combine the two, but we're not going to get that far. So we're just going to do the basics of this very fancy sounding term called linear regression. Okay, so here's the idea. We can use math to study how related two sets of data are to each other. So previously, we've really only ever studied like one set of data at a time, one thing at a time. But this is a very common thing. You'll see lots of graphs that do stuff like this on the internet. Okay, so here's some examples of what this can be. So you can ask questions like this. Is there a relationship between, and then you just say two numerical things, really. So how about this? How well someone does on a quiz and how well they do on a final or something, on a final exam. So you might expect that these two things are related. You would probably guess that if someone does better on a quiz, they typically also do better on a final. But using math, we can actually measure how related they are. So that's one example. But then there's much fancier things. This is a very big thing now. Is there a relationship between the amount of CO2? I don't know if the 2 is big or small because I don't know any chemistry, but amount of CO2 released in, sorry, just released, and the an increase in temperature. So this is something that has been studied a lot, and there is a relationship between these two. But then you'll have lots of people question this relationship because they learn one little phrase in math in a stats class, and they think they can be an expert in questioning things that they don't understand. So I'll talk about that later. Okay, so here there are relationships between the two things in both of these examples, and people have studied them. And it sort of like makes sense that there should be a relationship here. This one is not as clear until you like learn a bunch of science. But then using that same math that shows relationships between those things and those examples, you can still ask the same question about things that are seemingly not related. So for example, the amount of ice cream consumed, oops, can't spell today, consumed by people, I guess, versus the amount of murders. So is there a relationship between these two things? They don't seem related, but the math can tell us that these things are related. And that's the unfortunate part. So you can't just like conclude directly from the math that they are related, just that they're mathematically related. And you have to go further to see if it actually makes sense that one should impact the other. So another thing that people like to do is is try to use flawed conclusions from math that they don't understand to say that autism is related to all sorts of things. So put your favorite guess here, because people love to do this. Vaccines and all sorts of other stupid things that people believe. So I don't know, they'll just make up whatever. And the point is that just because there's some sort of mathy relationship between two things, that could hint at something, but you have to go deeper to actually figure out if they really are related, because they could be coincidentally related. Okay, so that's the kind of stuff we're going to be talking about. So we have to bring in fancy stats language. So roughly speaking, if two types of data go up or down together, then you might say that they are related. But very important, but, so underline 3 times. This does not mean, this is what I was hinting at before, this does not mean there is any reason to believe that one causes the other, or that they cause or impact each other. So this is what I was talking about before. This happens a lot. So you need further explanation. So people misuse this little factoid here in 2 different ways. They either don't know this factoid, so they immediately think that 2 things are related just because their data goes up or down together. That's bad. Or they think that nothing is ever related because they can just say this phrase. The phrase you'll learn is correlation does not imply causation. So they'll use that phrase whenever the math points to the 2 things being related, but they really don't want them to be related. So they want to like discount everything. So they'll just say that without actually understanding it. Okay, so let's do some math here. So the first thing we're going to learn about are scatter plots. So this is just a new type of graph, a new visual thing. So they're a visual way to represent 2 types of data together. So the best way to learn about them is simply just to jump straight into an example. So here's one. Okay, so let's pretend that an app has 0.5 million, so 500,000 users in 2000. Were there even apps in 2000? This question doesn't make sense. But then 20 million in 2002, 33 million in 2003, and 47 million in 2004. So what are the data, the 2 types of data being related here? Well, it's really just the number of users of this app is one type of data versus the year. So what we're doing here is we're thinking about how these 2 types of data are related, meaning as the number of users goes up or down, does the year sort of follow along in the same way? Well, this is where scatter plots come in handy. So to see how they relate, we can draw points, so actual points on a graph. So the old XY axis thing that you learned a million times. With the year, so typically time goes on the x-axis, so labeled as the x-axis. And users, number of users, as the y-axis. And this will be an example of a scatter plot once I finish drawing it. So let me put it over here actually. So it's right next to the data that I have. So it'll look something like this. I'm putting the year down here. I'm putting the number of users here. But because it's talking about millions, I'm also going to put it in millions so I don't have to write a bunch of zeros. So, okay, so of course it's a bit subjective how you draw it. I'm going to start the year at 2000, and then I'm going to go and just count by 1. So that'd be 2000, 2001, 2002, 2003. I guess I only need to go to 2004. And then for the users, I'm just going to go, I need to go about to 50. So I'm going to do 25 million and 50 million, halfway. Okay. So then what I'm going to do is I'm just going to draw a dot at each. So what are my points on this graph going to be? They're going to be the number of users as the year as the x-axis. So the year, comma, so that's the x-coordinate. The number of users is the y-coordinate. So for example, what are my dots going to look like? They're going to look like 2000. And then at the year 2000, we had 0.5 million. So it'll be that. It's the y value. And then I have 20 in 2002. And then 2003, I have 33. And then I have 47 in 2004. So these are the 4 dots, 4 points that I'm going to draw. Okay, so 2000, comma, 0.5. 0.5 will be super low down here. 2002, comma, 20, about right here maybe. 2003, comma, 33, maybe like right there. And then 2004, comma, 47, up there. It doesn't have to be perfect, you just do your best. So this lets us visualize how they are related. So what we're looking at here is we're trying to see if this forms a line type thing. That's going to be the idea. Okay, so if they form a line, what is this suggesting? So by line, I just mean something like nice and straight like that. And in this case, they sort of do form a line. It doesn't have to be a perfect line, but it's very line-ish. But the point is, what if they did form a perfect line? What would that suggest? Well, then that's saying that as one type of data goes over or increases, that the other type of data also increases at a proportional way. So that would be nice if they form a line. This would suggest that as one kind of data increases, so does the other in a proportional way. So proportional is the key word here, so that just means that the ratio is always the same. So every time x goes over by, so for example, 3, well, maybe y goes up by 10, and it keeps doing that same pattern. That's not exactly, I just made those numbers up. That's not for that example. Okay. So then what if the line was going down though? Well, so if the line looks more like this, then what would that be suggesting? Well, just that as the first one goes over, the other one goes down. So instead of saying so does the other, we would say the other decreases, still in a proportional way. So now the y is going down as the x is going up. But you would still say that they're related because as one does something, the other does something too, proportionally. Okay, so let's see some examples. All right, so here is a scatter plot of the number of ice creams sold, I don't know where this is, somewhere, and in that same city, the number of murders. So 5, 10, 15, 20, and 5, 10. So this one, they're going to be proportional in that they go up almost exactly the same together. So this is just an example, so I'm just going to sort of draw the dots very quickly without thinking too much about being perfect. Okay, so again, they don't have to be a perfect line, but the point is that it's line-ish. So here, the shape, what we're really looking at is the shape of the dots. And really to understand something, you have to see something that's not that thing. So this is something that maybe looks line-ish to you. So let's see something that doesn't. So, oops, how do you spell things? Well, something like this is not line-ish, and I'm going to bother with a real data 1, data 2. But if the dots just sort of went all over the place randomly, well, there's not really a line-ish shape to them. So line-ish is sort of like something you sort of look at and you decide on the spot. No, that's not really like a line. Yes, this one's like a line. So then the idea is that the more line-ish, the better. So we can see here, this one's pretty line-ish. It's pretty good. So line-ish is not a technical term, but we don't have a better term for it yet. Okay, so the more line-ish, the more strongly, that's the keyword that we'll come back to later, the more strongly that the data, the two types of data are linearly related, as opposed to other types of relationships. So for example, you might have two types of data where as one creeps over to the right, so as the x is increasing, the data 2 type, the y values, they go up super fast or something. So there, it's not really a straight line. You can imagine if it just went super high up, it's not really a line at all. It's much more exponential. So this would be called. So this would be called exponentially related, but we're not really going to study those types of things. We're only going to have time for lines. So that's all we have to worry about, luckily. And lines are the best because they're the easiest. So we're just going to study linear relationships. All right, so here's another example. Let's plot the following exam scores of 11 students, and then we'll go ahead and try to do some other stuff. So the 2 exams I'm going to use as my X data their first exam. So that's the first type of data. And then as their Y, their final exam. So this is something that teachers like to study, is if how you do in your first exam is related to how you do in your last exam. Okay, so real quickly, I'll write these down: 65, 67, 71, 71, 66, 75, 67. I should have just popped it in. In fact, I will do that now. Whoops. Okay, so here are the exam scores, and I'm just going to make a scatter plot, so nothing too fancy. And so I'm putting their first exam on the X axis and their final on the right. So it's not in a good order or anything, so you sort of have to go through it and see that it might be a good idea to start at 60 and then count by 5s down here. And then for the final, I'm going to count by 50s. Okay, and then I'm just going to plot all these points. So for example, this is going to tell me that I should plot 65, comma 175. So 65, comma 175 is about right there, for example. And then I'm going to do all of them. Maybe I'll do a couple in different colors just to show you. So 75, comma 198. So 75, and then I go up to 198. It's going to be very hard because you have to sort of eyeball everything, but you just do your best. I'll do one more with a color, picking a nice round number so I can at least get one of them right. So 70, comma 163. So that would be around there. Okay, so the rest I'm just going to pop in so I don't have to show you every single one. Okay, so here's my terrible plotting of these points. So it's a good time to point out that you can always use computer programs to graph things like this for you, and it'll look much nicer when you want to do real work. And that's what real stats people do. So you can use Excel, for example. It's a lot of people do. Okay, so in any case, so when the data looks lineish, which it sort of does here, we can do more cool stuff. So I would say it sort of looks lineish here. What this really means, so I can stop using the word lineish, this means we can draw a useful best fit line. So useful, we'll get to in a second. A best fit line is just a line that goes through the data in a very special way. Through the data. So what is it? Which is, it has a very technical term, but, and I'll say it, it's the line that minimizes the total distance to all the points. And to really know how to make this line, you got to like learn calculus and stuff. But for us, we're just going to eyeball it. So it's the line that minimizes the total distance to all the points. And so let me just draw a different example before I bother doing that example to make it more clear what this kind of thing looks like before I do it in the real one. So for example, if I have these points here, so I'll make something very line-ish, very clearly line-ish, then what would the best fit line look like? Well, it would look something like this. Because that line is making the distance from each point, so for example, that distance to the line, very small. That distance to the line is very small. That distance, all of these distances are very tiny. So it's minimizing all those distances to each point. And so it's minimizing the total amount of blue you see here. And there's a very technical way to actually create this line that we're not going to get into. We're just going to eyeball it. So this is a pretty good estimate, I think, because I tried to make it very line-ish so it'd be easier for me to draw it. So this would be very close to the best fit line. So if you're asked to draw a best fit line, you can just sort of eyeball it in these problems because it's going to be very line-ish. So as opposed to something like this is very much not the best fit line, not even close. So the reason being, like, all of these distances are very far away. So it's not minimizing those distances at all. But really, you can just eyeball it. It's the line that goes through the data the best. That's one way to think about it. So now if I do it up here, it's going to look something like this. It's got to be a straight line, so try to make it as straight as possible. But in any case, that's fine. So you just really eyeball it. It goes through close to as many points as you can. It's a good way to pretty much get it right. So yeah, a computer or a calculator can draw it perfectly, the actual best fit line, but you can just eyeball it. Okay, so it is a line in the end though. So what does that mean? So this is actually a line. Remember stuff about lines that you learned a long time ago? That means it looks like it has a line equation, so you can write it as y equals mx plus b. So here, this one turns out to be, again, you don't have to calculate the line because you have to use calculus for that. You just have to be able to draw it. But this one will turn out to be, if you actually go and calculate it, it'll be this, 4.83x minus 173.51. Now you got to remember a bit about lines. So remember that this number here is the slope. That's what m is. And that's just saying how far up the graph is going per unit that it goes over to the right. But then the point of having this line is you can use it to make predictions. That's the nice stuff. So, for example, I could say, well, if somebody gets an 80, here, now I can sort of estimate that they might get near there because that's where the line is going to go through if I continue drawing the line. And that's the idea. But with the actual equation, I can, instead of eyeballing it, I can actually do that. So how is that going to work? Well, we can predict the y using the x is the idea. So we can predict how someone might do on the final. That's the y value, given a certain score on the first exam. That's going to be their x value that they in this line. So for example, someone gets a 60 on the first exam, that's your x. And then we predict y just by plugging it in. So all we're going to do is stick 60 in here. So 4.83 times 60 minus 173.51 equals 116.29. And if they got like a 72, on the first exam, we would predict using this line that they might get around, so you do 4.83 again, times 72 now, minus 173.51. You'll predict that they get around a 174.25. That's the idea. And next time we'll do some other stuff involving correlation, which is a fancy word I said at the beginning of this lecture, but we're not going to talk about it today. So the point of today is just plotting scatter plots and making best fit lines. And then if I give you the line equation, you can use it to make predictions of about the second data from the first data. So of course this makes a lot of assumptions. So this is saying that just because there's a linear relationship, you can now say that the x is somehow impacting the y, and that's why you can use this line to make predictions. But that's not necessarily true, because you could have lots of other situations. So just to be aware of the things that go wrong. So I don't know, you might have something like this, a very line-ish type thing. So you'll say, okay, I'll draw a best fit line, do your best, and then I'll predict something over here using that line. But then in reality, it turns out something maybe changed, and now all the data started looking like this afterwards, and you didn't know. So there's a lot more to this stuff than just making a line and then making a prediction. But we're not going to have time to get into deeper things. The point is, you can't just do too much. You can't overvalue the stuff we're doing here and try to use it to solve a million different things, because a million different things could happen instead. Okay, so I will see you next time.